Hello, welcome to another module in this massive open online course. So, we are looking at the mathematical preliminaries for optimization, alright, and we have looked at the eigenvectors and eigenvalues. In this, we will start looking at a different type of matrices known as positive semi-definite and positive definite matrices. So, we are going to look at the properties of and definition of positive semi-definite and as well as positive definite. Positive semi-definite and positive definite matrices, and this is often abbreviated as PSD matrix, and this is often abbreviated as a PD, positive definite matrix. A matrix can be positive semi-definite matrices, that is there can be positive semi-definite matrices and positive definite matrices, okay. And of course, both of these are also defined once again only for square matrices, alright, similar to the concept of eigenvalues and eigenvectors, these are defined for square matrices, okay. So, also defined only for square. Okay. Now, now matrix A, consider a matrix A. Consider a square matrix A. Now, if for the real case, if x bar transpose A x bar greater than or equal to 0 for all x bar, then A is a positive semi-definite matrix, okay. So, x bar transpose A x bar is greater than or equal to 0. Now, if x bar transpose A x bar is strictly greater than 0 for all x bar, then A is a positive definite matrix. So, this is positive semi-definite and positive definite matrix. If x bar transpose A x bar is greater than or equal to 0, right, for all x bar, all vectors x bar, then it is positive semi-definite. If it is strictly greater than 0, then it is positive definite. Now, these are for real vectors and real matrices. Now, for complex vectors and matrices, now this definition is for now for complex vectors for matrices, as we have seen before, we have to replace the transpose by the Hermitian. So, x bar Hermitian x bar greater than or equal to 0 for all x bar implies positive semi-definite, and further x bar Hermitian x bar strictly greater than 0 for all x bar implies a positive definite matrix. So, this definition is for complex matrices and vectors. Let us take a simple example to understand this. Consider a square matrix. Consider a square matrix A equals 2, 6, 6, comma 18. Let us consider the square matrix 2 cross 2 square matrix 2, 6, 6, 18. Now let us look at x bar transpose A x bar. This is a 2 cross 2 matrix, so the vector x bar will be 2 dimensional x1 x2 times 2, 6, 6, 18 into x1 x2, and this is equal to, you can see this will be equal to, well, this will be equal to twice x1 square when you multiply this out plus 18 x2 square plus 12 times x1 x2, and this will be equal to, you can easily check, twice x1 plus 3 times x2 square, which is a perfect square, and therefore, this is always greater than or equal to 0. Hence, hence now you can see this also, this is not strictly greater than 0, because 2x1 plus 3x2 equal to 0 if x1 equals minus 3 over 2 x2, alright. So, this is only greater than or equal to 0. If 2x1 plus 3 equals 0, then this will be 0, that is x bar transpose x bar will be 0, otherwise it is greater than 0. Therefore, in general it is greater than or equal to 0, hence the matrix A is positive semi-definite. Hence, this matrix, hence A is positive semi-definite. Since x bar transpose A x bar is greater than or equal to 0, is greater than or equal to 0 for all x bar. Let us look at a property of this positive semi-definite. Let us look at a very interesting property. Let us look at an interesting property of this. Now, consider the eigenvalues. Since these are square matrices, eigenvalues. So, the eigenvalues, if A is positive definite, then the eigenvalues lambda I of A, denoting this by lambda I bracket A, these are strictly greater than, all the eigenvalues have to be greater than 0. On the other hand, if A is PSD, then the eigenvalues are greater than or equal to 0. That is, some of the eigenvalues can be 0 and rest of them are greater than 0. Okay. So, this is an interesting point. For a PD matrix, the eigenvalues are strictly greater than 0. For a PSD matrix, the eigenvalues are greater than or equal to 0. Again, let us verify this property on the previous example. So, let us look at A. Again, let us look at the example. A equals our matrix 2, 6, 6, 18. Now, to calculate the eigenvalues, one has to consider the characteristic polynomial, determinant of A minus lambda I, which is the determinant of two minus lambda 6, 18 minus lambda and this can be simplified, the determinant can be simplified as 2 minus lambda times 18 minus lambda minus 36 equal to 0, and this is the characteristic equation. Okay, remember the characteristic polynomial and the characteristic equation for the matrix. This implies, now if you simplify this, this implies 36 minus 20 lambda plus lambda square minus 36 equal to 0. This implies lambda square minus 20 lambda equal to 0, which implies lambda square, which implies lambda square equals 20 lambda, which implies lambda equals 0 comma 20. These are the two eigenvalues. Okay. So, you can see, in fact, what you can see is very interestingly that one of the eigenvalues is in fact 0, correct. If you call this lambda 1 is in fact 0. One of the eigenvalues is 0. This implies, in fact, you can also see, and we also checked that the matrix is PSD, positive semi-definite. Now, for a symmetric matrix, if the eigenvalues are greater than or equal to 0, matrix, one can also conclude that that is not only the forward property, but also the reverse, that is right, that if for a symmetric, that is for a symmetric matrix, if the eigenvalues are greater than or equal to 0, the matrix is positive semi-definite. If the eigenvalues are greater than 0, the matrix is positive definite. For symmetric matrix A, it is an interesting property. For a symmetric matrix A, if eigenvalues lambda I of A greater than or equal to 0, then A is positive semi. If lambda I greater than or equal to 0, then A is positive semi definite. If lambda I A is greater than 0, then A is a positive, definite matrix. Let us now continue looking at another important concept, that is of the Gaussian random variable, which we are also going to use frequently in our framework of optimization. Okay. So, we want to look at the basic concepts of Gaussian random variables, which are central to our discussion on optimization. So, what is a Gaussian random variable? Well, x is a Gaussian random variable. X is Gaussian random variable with mean equal to mu and variance equal to sigma square, that is, it is denoted by this notation, Gaussian, this is also known as a normal random variable. It is denoted by this notation n mean script n mean mu variance sigma square. Okay. And the probability density function of this, every random variable has a probability density function that is given as 1 over square root of 2 pi sigma square for the Gaussian random variable e raised to minus x minus mu whole square by 2 sigma square. What is this? This is basically your PDF or the probability density function. PDF of the Gaussian random variable with mean mu and variance equal to sigma square. Okay, so this is the probability density function, and you might also recall that many of you might be familiar that the shape of this probability density function is given by this bell shaped curve with the peak occurring, that is the peak of this occurs at x equal to mu, that is the mean, and the spread of this is controlled by the variance equal to sigma square controls the spread. So, the peak occurs at the mean. So, the peak shifts the Gaussian probability density function and it is symmetric about the mean, it is a bell shaped curve, and the spread of this is controlled by the variance. For instance, if the variance decreases, then the spread decreases, the Gaussian probability density function becomes more and more peakier, that is more and more concentrated around the mean. Okay. So, as the variance decreases, it becomes more and more concentrated around the mean. Okay. As the variance decreases, it becomes concentrated around the mean. Okay. And now one can define a new random variable x tilde by subtracting the mean and dividing by the square root of the variance or sigma, which is the standard deviation. Okay. So, now you can see this x tilde is also, which is derived by subtracting the mean and dividing by the standard deviation sigma. Now, this x tilde is also a Gaussian RV, and there is something interesting about x tilde. The mean of x tilde will be 0, that is expected value of is 0, and the variance, that is expected value of x tilde minus mu or x tilde square in this case, since mean is 0, is equal to 1. So, mean equal to 0 and x tilde is Gaussian RV with mean 0 and variance unity. Okay. So, this is a Gaussian RV with mean equal to 0 and variance equal to 1. Such a Gaussian RV with mean equal to 0, variance equal to 1, this is termed as the standard normal random variable. Standard normal this is termed as the standard normal random variable. Okay. and now we define, now this standard normal random variable is used to define what is known as the Q function. So, this now the probability density function of the standard normal random variable, that is also simple to design because it has mean mu equal to 0 and variance 1. So, you substitute mu equal to 0 and sigma equal to 1 in the earlier expression for the probability density function of the Gaussian random variable, and what you get is the PDF of this standard Gaussian random variable given as 1 over square root of 2 pi, since sigma square equal to 1 over square root of 2 pi e raised to minus x tilde square. Remember mu is 0, so x tilde minus mu is simply x tilde square divided by 2, again once again sigma square equal to 1. This is the PDF of the standard normal. And one can define the Q function of the PDF of the standard normal, that is the probability that the standard normal Gaussian random variable x tilde is greater than or equal to a quantity x naught is denoted by Q of x naught. This is also termed as the Q function or the Gaussian Q function. This is the probability that the standard normal variable x tilde is greater than or equal to x naught, which is given by the integral x tilde x naught to infinity, the integral of the probability density function of the standard normal variable 1 over square root of 2 pi e raised to minus x tilde square divided by 2 times d of x tilde. That is the probability that this is also equal to the probability that x tilde belongs to the interval x naught comma infinity. Okay. That is basically what we are asking is the question, what is the probability that x tilde, the standard normal random variable, takes a value greater than or equal to x naught, or basically that it lies in the interval x naught to infinity. And that is, remember, the probability that the random variable lies in a particular interval is given by the integral of the probability density function of the random variable over that interval. So, therefore, it is given by integral x naught, this probability is given by the integral x naught to infinity 1 over square root of 2 pi e raised to minus x tilde square divided by 2 dx tilde. Okay. And what it denotes, as I have already told you, it denotes the probability that this Gaussian random variable with mean 0 and variance equal to 1 is greater than this quantity x naught. So, it denotes the probability that, or the area under the PDF greater than or equal to x naught. This is also known as the tail probability of the standard normal random variable. This is also known as the tail probability of the standard normal. There is probability under the tail starting from x naught. This is also known as the complementary cumulative density function. The cumulative density function gives the probability that the random variable takes value less than x naught. The complement of that, or 1 minus the CDF, gives the probability that it is greater than or equal to x naught. This is therefore known as the complementary cumulative also known as the complementary cumulative distribution function, or the CCDF of the standard normal random variable. Now, let us come to a multivariate Gaussian random variable or a Gaussian random vector. a Gaussian random vector with multiple components, each of them individually Gaussian and all of them being jointly Gaussian. Okay. So, we will talk about a multivariate Gaussian RV Now, a multivariate Gaussian RV is given by x bar equals x1 x2 up to xn, and this is a Gaussian random vector x bar this is a Gaussian random vector x bar and x bar equals x1 x2 xn. So, this has n components. We will denote the mean. Now, each of the components is going to have a mean. So, the mean is going to have a be a vector, that is expected x bar equals the expected value of each of the components. So, this is going to be an n dimensional vector, which we will denote by this. Let the mean of the various components be mu1, mu2 up to mu n. So, this is basically your mean vector. So, the mean is going to be a vector. So, you can call this also as the mean vector of the multivariate Gaussian random variable. And further, instead of the variance, we have the we will have the covariance matrix, which looks at the variance of each component and also the cross covariance, also the covariance, correct, the cross correlation corresponding to each of the elements of this random vector. And the covariance matrix is defined as follows, that is R equals expected value of x bar minus mu bar into x bar minus mu bar transpose. Okay. And this is, remember, this is termed as the covariance matrix. This is termed as a covariance matrix, and this is an n cross n matrix. This is termed as a covariance matrix and this is an n cross n matrix, and the probability density function of the multivariate Gaussian random variable and you can also denote this as n again. So, the multivariate Gaussian random variable you can denote it as Gaussian random variable with mean vector mu bar and covariance matrix R, and the probability density function is given as 1 over square root 2 pi raised to the power n raised to the power of n. The determinant of the covariance matrix R times e raised to minus half x bar minus mu bar transpose R inverse x bar minus mu bar. Okay. And this is basically your PDF of the multivariate Gaussian random vector, PDF of multivariate Gaussian vector with mean equals mu bar and variance equal to covariance matrix. And covariance matrix equals R. Okay. all right, and that is the expression for the PDF of the multivariate Gaussian random vector. Let us now look at an example to understand this, and let us look at an interesting special case of this multivariate Gaussian random vector, which is when the different components of this Gaussian random vector are independent. So, consider a multivariate Gaussian with expected x bar equals mu bar equals the 0 vector and expected value of xi into xj, the different components, is equal to 0 if I not equal to j and sigma square if I equal to j, all right. So, the what we are seeing is the cross correlation expected value of xi xj if I not equal to j is 0, all right, and all the variance of each element is sigma square. So, these are basically what you can see is basically these are known as uncorrelated random variables because the correlation is 0. So, these are basically uncorrelated. Uncorrelated Gaussian random variables is the cross correlation, cross covariance is 0. These are uncorrelated Gaussian random variables. Okay. And now, if you compute the covariance of this, that will be given as, or the covariance matrix of this, that will be given as, well, we already seen, that is x bar minus mu bar into x bar minus mu bar transpose. Now, mu bar is 0. So, this will simply be expected value of x bar into x bar transpose, which is now, let me write it in terms of its vector. This is going to be expected value of x bar, which is the vector x1, x2, xn into the transpose x1, which is the row vector. Remember, transpose of a column vector is a row vector. And now, once you compute this, what you will observe is, if you compute this, you will have entries such as x1 square, the off diagonal entries will be x1, x2, x2, x1, x2 square, and so on. And now, if you look at this matrix, expected value of each element on the diagonal, expected value of x1 square, x2 square, x3 square, so on is sigma square, but the expected values of the off diagonal entries x1, x2, x2, x1, so on are 0, because these we have considered the random variables to be uncorrelated, and therefore, the covariance matrix basically you can see reduces to sigma square. All the diagonal elements are sigma square, the off diagonal elements are 0, and therefore, this is also sigma square times identity. And now, once you compute, so our covariance matrix equals sigma square times identity. This is, remember, this is our covariance matrix, and therefore, the multivariate Gaussian probability density function is given as 1 over square root. Now, if you look at the determinant of this, determinant of r is sigma square times identity, determinant of r is sigma square raised to the power of n, which is sigma to the power of 2n, and therefore, the probability density function is 1 over, let me just write it separately, is 1 over square root of 2 pi raised to the power of n sigma raised to the power of 2n, that is the determinant, times e raised to minus half x bar minus mu bar, that is x bar transpose R inverse. R is sigma square identity, R inverse is identity divided by sigma square times x bar, which is, now you can simplify this as 1 over 2 pi sigma square raised to the power of n by 2 times e raised to minus half or 1 over 2 sigma square x bar transpose x bar transpose identity, x bar is x bar transpose x bar. But recall x bar transpose x bar, recall x bar transpose x bar equals norm of x bar square, which is also equal to x1 square plus x2 square plus so on up to xn square for a real vector x bar, and therefore, this is also equal to 1 over 2 pi sigma square to the power n by 2 times e raised to minus 1 over 2 sigma square norm x bar square, and this is also equal to 1 over 2 pi sigma square n by 2 e raised to minus 1 over 2 sigma square summation 1 equal to I to n x I square. And interestingly, now you can also write this as the product I equal to 1 to n 2 pi sigma square, or 1 over, you can also write it as 1 over square root of 2 pi sigma square e raised to minus x I square divided by 2 sigma square, and therefore, now this is the product symbol similar to summation, this is your product symbol, product I equal to 1 to n, and now you see these are the individual PDFs, these are the individual Gaussian PDFs of the various random variables xi with mean equal to 0 and variance equal to sigma square. And therefore, what you are seeing is that when these Gaussian, when these component Gaussian random variables are uncorrelated, the joint Gaussian, the multivariate Gaussian PDF equals the product of the individual PDFs, which means that these PDFs, these random variables are not only uncorrelated, but they are also independent, and this is a unique property of the Gaussian random variable. If two Gaussian random variables are uncorrelated, they are also independent. This is not true for any general random variable, it is an interesting property that is applicable only for the Gaussian random variable. So, this implies that the Gaussian RVs are also independent. Okay. So, for a Gaussian RV, uncorrelated implies that they are independent. However, this is not true for any general random variable, and this is the important property, not true for but the other way around is always true, right? For any random variable, if they are independent, if two random variables are independent, then they are going to be uncorrelated. However, it is in general, it is only for a Gaussian random variable, it is true that if they are uncorrelated, they are also independent. This is not true for any general random variable. All right. So, this small example illustrates this interesting property of the multivariate Gaussian random vector. Alright. So, we will stop here and continue with other aspects in the subsequent modules. Thank you very much.